Hello everyone. In today's session, we are going to study types of stress and strain. This is basically the first topic of the chapter Simple Stresses and Strain of the subject Strength of Materials. These are some of the outlines of today's session. We will start our session with the definition of rigid body and deformable body, and then we will define strength of materials. From here, you will get a motivation why we are going to study this subject strength of materials. Later on, we will study stress and strain and then the types of stresses and types of strains. So let us start the subject. Let us start the new subject strength of materials or mechanics of materials. First, we want to discuss what is actually strength of materials. But before that, you should know some basic terms which are used in strength of materials, and one of the term is rigid body. What is a rigid body? A rigid body is that body which do not deform under the action of applied forces. It means you are applying some external forces and the body is not getting deformed. It means the dimensions of a body, which is a rigid body, do not changes with the application of forces. A body which do not deform under the action of applied forces. But do you think that really a rigid body exists? Because if the force is very large, the body will certainly deform. So when we say rigid body, it means we are saying a limit of forces. Under certain limit, the body is acting like a rigid body. After certain limit of forces, the body may not be a rigid body. It means we are mainly concerned about the deformable bodies. In strength of material, our main aim will be to discuss the deformable body, the strength of deformable bodies. So what is deformable body? A body which deforms under the action of forces. So if I make a diagram and suppose this is a bar of certain length L and we apply a force P to this bar, there is certainly some deformation in this bar, and suppose this deformation is delta L. So what will happen if I remove this force P? If this P force is removed, what is going to happen? If the force is within certain limit, lower forces are there, that limit is called elastic limit, the body will regain its original position. So within certain limit, that is called elastic limit, the body will regain its original position, means this deformation will vanish. So what is that force? What is that force which is causing the regainment of the original dimensions, which is causing vanishment of this deformation? It means there is certain internal force developed which is resisting this force, which is opposite to this force, resisting force developed in this material against the applied force. So we have applied the force P and we have obtained a resisting force P dash in this material. So P dash is the internal force, or this is also called resisting force, and P is the external force or applied force. We have applied force P and we have obtained the resisting force P dash in the material. I am showing here a certain particle which is placed at certain cross-section area, suppose A. But from where this P dash came? From where this P prime internal force came? So molecules have cohesive forces, cohesion property is there. If the material is of same molecules, then there is cohesive forces, attractive forces, and if the material is of different molecules, then there is adhesive forces. So adhesive forces belongs to different materials, different molecules of the material, and cohesive forces belongs to the same molecules of the material, right? So if this is uniform, this material is uniform throughout this cross section, so we can say that there is some cohesive forces developed in the material, and that cohesive forces are resisting when the particle, when this force is trying to deform this body. It means, so this resisting force is just opposite to this external force, and higher this resisting force, higher will be the strength of material. If we go on increasing this, if we are going increasing this external force, this P dash also go on increasing, but there is certain limit. After that limit, this P dash will no longer will able to sustain this deformation, and there will be a permanent deformation in the material after the removal of this force. So within elastic limit, if we remove this force, there is this deformation will be regained, and the original dimensions will be regained, and there is permanent vanishment of this deformation. But if this force is high, there may be chances that there is some permanent deformation in this material. So what is then strength of material? The strength of material is related to this force P dash, which is resisting force. If we go on increasing this external force, the resisting force also go on increasing. So if it can bear a higher P dash, higher resisting force, we say that material have a higher strength. And if this P dash resisting force is low, so we say that the material has lower strength. So what is strength of material then? Now we can define the strength of material. So this is the ability of a material, to resist the deformation. And higher the resistance to this deformation, higher will be the strength of the material. Now you can understand that what we are going to study in this subject, that is the strength of material, that is ability of a material to resist the deformation. But this is very qualitative term. We can compare two materials using strength of material, like mild steel has higher strength compared to rubber, so strength of mild steel is higher, strength of rubber is lower. But how to quantify it? What is a quantitative, what is a numerical methods, numerical formula for using this strength of material? So that is the term which is very important in this entire subject, that is stress. What is stress? Stress is basically the numerical or quantitative value of this strength of material. So what is stress? In our day-to-day life, we generally use this term stress. Like you are working in a company and you say that I have a very large workload, a lot of workload is there at your head, and due to that workload you are getting stressed. So there is sleepless nights due to this stress. So workload is external and you are getting stress in your mind. So something is external and you are getting stress internally. Same is the case with the strength of material. We have applied some external force, and due to that we are getting some internal force or resisting force, that is causing stress in the material. So when this force is acting, this internal force is acting at certain area of cross section, we are getting stress. So what is stress? How it is defined? This is the internal force. This is not external. This is internal force or resisting force or in another term we can say resisting force per unit area. So this force per unit this area is causing the stress in the material. So this is stress, that is P prime upon area. This is the stress which will be widely used in this subject. But as we said that within elastic limit, if you remove this force, we will get the original dimensions of the material, means it has regained its original position. How it has obtained the original position? Because P was equal to P dash, that's why delta L is vanished. So within elastic limit, these two forces, the applied force and the resisting force, should be equal. So we can say within elastic limit, P will be equal to P dash. P will be equal to P dash, means external force should be equal to internal force. And if this is the case, then we can further define sigma as P upon area, external force per unit area. Actually, by definition, stress is internal force or resisting force per unit area, but because within elastic limit we can say P is equal to P dash, so we can write stress equal to external load per unit area. So what is the unit of this stress? That is Newton, which is the unit of force, per unit area, that is meter square, or Pascal. 1 Newton per meter square is equal to 1 Pascal. When I say PA, it belongs to Pascal. Our next topic is types of stresses. We have already studied about the stress, that what is stress. Now we want to study how many types of stresses are there. So types of stress, right? Basically, the stress, we have seen that this is the force per unit area, force acting on a given area. So stress types can be divided into two parts, that whether the force is acting on the normal to the area or parallel to the area. If it is acting at the normal to the area, we are saying that this is a normal stress. And if it is acting at the parallel or transverse cross section of the area, then we said that this is a shear stress. So we have two types of stresses, normal stress and shear stress, right? So two types of stresses are there. This is a normal stress and shear stress. Normal stress is acting on the perpendicular to the area, and shear stress is the parallel to the area. These stresses can further be divided into tensile and compressive. Like normal stress may be tensile, may be compressive. So this is tensile stress and compressive stress. Depending on whether the force is tending to elongate the body or shorten the body, right? Tensile stress, suppose this is a bar and the force is acting normal to the cross section like this, and it is tending to elongate the body, increase the length of the body. So there will be certain increase in the length of the body. Suppose this is delta L. Delta L is the increase in length of the body. So we will say this is a tensile stress because it is getting tension in the material, right? So this is tensile because the body is elongating or increasing length in the body, right? And in compressive stress, there is decrease in length of the body. There is force is tending to shorten the body. So there is decrease in length of the body. This is delta L. Decrease in length of the body. So we will say this is compressive stress will be developed in the material. If we see a particle, this is the stress developed sigma in the material. This is tensile stress, and the stress developed in the material here is compressive stress, right? Like this, isn't it? So this is the tensile stress. This stress I have shown on a particle. If you want to show on the entire cross section, so you can also show on the cross section also, complete cross section like this. So on this cross section area you can show here the stress developed is like this. This is another way of showing the stress, that this body is stressed, some stress is developed in the material on this area. Or you can also show on a particle also, on a given certain particle, because there are many particles are there, right? Also here also you can show the stress on a given cross section area also, complete all the particles like this. So this is another way of showing the stress, compressive stress. So this is the tensile stress and this is the compressive stress, and this is the way of showing the tensile and compressive stress, right? What is shear stress? When the force is acting parallel to the area, like this is a block placed on a on ground or earth, and a force is applied parallel to the cross section like this. This is a P, right? So I'm highlighting this area. This is the area at which this force is applied. This is the area, this area A. So stress developed in this material will be shear stress, because it is trying to shear off the material, So stress developed, this is shear stress is denoted by tau, and this will be equal to load upon this area which is highlighted here, this area, upon area. This is shear stress. And tensile stress, as usual, as we have already read, that stress will be equal to load per unit area. It may be tensile, it may be compressive, depending on what type of load, whether it is trying to elongate or shorten the body, right? So we have normal stresses, we have shear stresses. Normal stresses acting on the normal to the area, shear stresses acting on the parallel to the area, right? Now, tensile stress and compressive stress can be developed by directly applying the forces or by bending the beam. Suppose this is a beam, this is a marker, and suppose this is a beam, flexible beam, and we apply a bending moment to this, right? So this is Hooke bending moment, suppose we have applied. There may be two types of bending moments are there. Later on we will study that, Hooke and sagging. Suppose we have applied a Hooke bending moment, so that the upper part of the body get into tension and its length increases, and lower part of the body shorten length, and there is compressive stress developed in the body. So tensile and compressive stress may be developed by bending the body or by direct stresses like this, right? So tensile and compressive stress may be direct stresses, as we have shown here. These are direct stresses, direct stress, and this is also direct stress, and we can also obtain tensile and compressive stress by bending a body, right? So I am showing here a picture of bending. I am saying bending stress. Bending stress is a separate chapter we will study later. Bending stress. What is bending stress? I will show it by pictorial view. Suppose this is our beam, and a Hooke bending moment is applied. A Hooke bending moment is applied, and this is the neutral axis. Suppose neutral axis, and suppose I am showing here this part is A, this part is B, and this part is suppose C, and this part is say D. So what will happen? It will bend, because we have applied bending moment, right? And due to bending, what will happen? I am showing here what will happen to this. There will be increase in length of the upper part, because this is Hooke bending moment, and there will be decrease in the length of lower part, right? And this is neutral axis, and this AB part becomes A dash B dash, and CD parts become C dash D dash, right? So what is happening here? How the AB part is elongated, how the length of the AB is increased? because there is some tensile stress developed in the material, upper part of the material. So in upper part of the material, there is some tensile stress developed. This is neutral axis actually, and neutral axis is neutral. So this is tensile stress developed in upper part of the material, and at the same time in the lower part of the material, bending stresses, compressive stresses are developed. You can see here, in the lower part, compressive stresses are developed. So sigma T is here the tensile stresses, and sigma C here is compressive stresses developed in the material. Here it is compressive stress, sigma C. So sigma C belongs to compressive stresses and sigma T belongs to tensile stresses, and this is neutral axis, which is neutral. No stresses will be developed in this neutral axis. At the center there is no stresses developed at the neutral axis, right? And A belongs to neutral axis. So in bending also, tensile and compressive stresses are developed, and this is also normal stresses because this is normal to the cross section, right? So the another way of developing tensile and compressive stresses is bending stresses. So tensile and compressive stresses or normal stresses can be developed by direct stresses, as applying directly the forces, or by bending a beam like this. We have bent the beam and then we have obtained the tensile and compressive stresses at the normal to the cross section. How the shear stresses can be developed? We can apply direct shear stress like this. This is direct shear. This is direct shear. This is direct shear, right? Or we can apply shear stresses by torsion of shafts. So what we can do in torsion of shafts? There is a, suppose, shaft which is rotating and a torque is applied to it like this, and this torque is basically twisting this body, right? Shearing off. You can see here there is some shear of phenomena happening in this. So we can say the shear stresses are developed. So you will see that in the upper part, you will see that there is shear stress developed, and in lower part also the shear stress will be developed, right? And shear stress are always complementary, we will study later on. So shear stresses will be developed in this material above the neutral axis and below the neutral axis. So torsion of shafts also produces shear stresses. Later on, this is a separate chapter, we will study this chapter separately. So basically here, in types of stresses, I am going to summarize it. We have seen normal stresses and shear stresses. Normal stresses are of two types, tensile and compressive, and shear stresses simply acting on the parallel to the cross section, and this is normal to the cross section. Tensile stresses and compressive stresses can be derived by direct loading, or this is called direct stress, or by bending the beam, and we got the bending stresses. Shear stresses can be developed by direct shear. This is the direct shear. We have applied a shear stress directly, and this direct shear is shearing of the body parallel to the surface, and this stress is developed in the material. Or this can be developed by twisting the shaft, by giving a torque to the shaft, so torsion of shaft, and by torsion of shaft this is shear off, and the shear stress is developed at upper part of if there is a central axis, and above the central axis and below the central axis shear stresses will be developed. Later on we will study this separately as a chapter. For the time being, in this chapter, simple stresses, we are going to study direct stresses like this, direct normal stresses and direct shear stresses. This is a separate chapter, we will study later. Now we want to study what is strain. Let us see the same figure again. We have applied a force P to this body, and there is some change in length of the body, say delta L, and the body was having a certain original length L. L was the original length of the body. So original length of the body was L, and there is some change in length of the body that is delta L. So to this original length, there is some deflection in the material. So strain is defined as what is the change in length per unit original length. So strain is defined as change in length per unit original length. Original length. What was the original length? That was L, and what is the change in length? That is delta L. So this is strain. So strain is given as change in length upon original length. So this is the definition of strain, right? And similar to stress, as we have discussed, the types of stresses, tensile, compressive and shear. Similar to that, there are corresponding to tensile stress, there is tensile strain. Corresponding to compressive stress, there is compressive strain, and corresponding to shear stress, there is shear strain. So we have types of strain. Types of strain. These are, first is tensile strain. Tensile strain, when the forces are acting in such a way that it tries to elongate the body. So the same figure I am making here to show that this is tensile strain. So this is our body, and there is some change in length of the body, and there is some deflection in the material, and this deflection is increasing the length of the body. There is some increase in length of the body. So our strain will be defined as delta L upon L, and you will see that this is positive because it is increasing the length of the body. I am showing that it is increasing the length of the body. So this is tensile strain. This is tensile strain. Second is compressive strain. Compressive strain. Compressive strain, the force is acting in such a way that it is trying to compress the body so that there is decrease in length of the body. Suppose this is the decrease in length of the body, delta L, and there is some original length of the body was L. So again, strain will be defined as that will be equal to change in length upon original length, but in this case this is negative because the change in length is decreasing, so it is basically negative or decreasing the length of the body or decreasing strain, right? So this is tensile strain, this is compressive strain. The symbols are same, you can see here formula is same, but it is tensile increasing positive and it is negative, right? I'm not writing here negative, but it is negative in the sense that the length of the body is decreased, right? And third is shear strain. So shear strain acts when a body is applied, parallel forces are applied to a body. So you can see here, suppose this is our body and some parallel force or transverse force is applied to the body at certain cross section area. So there is some change in length of the body. Suppose this is the shear off, after shear off it is making some angle, suppose phi at this point, and this was the length L, this was the length, original length, and there is some change in length parallel to this area, delta L. Delta L is the parallel to area and original length was this L. So we will say that shear strain, I am writing shear strain here. Later on I will, in this lecture only I will show how the shear strain is symbolized by this phi, but I want to show you that how this phi is coming. So shear strain will be equal to change in length delta L upon original length L, right? And in this figure I am making the figure here. In this figure, this is L, this is delta L, and this is phi. What is tan phi? Tan phi. What is tan phi? In this figure, this triangle, one triangle I have taken, change in length is delta L, length is L. What is tan phi? This is also equal to delta L upon L, perpendicular upon base, delta L upon L. So these two things are same. Shear strain is delta L upon L, tan phi is also delta L by L. So we can say that the shear strain can be written as tan phi, that is equal to delta L upon L, and for small angles, if the angle is small, which is the case with metals, most of the cases metals the small angle is small, so tan phi is nearly equal to phi. You know that for small angles tan phi and phi are same. So we can write that phi is equal to delta L upon L. This is the shear strain, and this phi is the symbol. This angle is basically the shear strain. This angle, this is shear strain. So this is shear strain phi delta L upon N. So here this phi is shear strain, shear strain phi.